Okay, so welcome to the seventh TA session of this NPTEL course, Principles of Signals and Systems, offered by Professor Aditya Jagannathan from IIT Kanpur. So my name is Yashvanth, and I'm a Ph.D. student at the Indian Institute of Science, Bangalore. And my research interests broadly lie in signal processing and applications in wireless communications. So I currently focus on designing and analyzing intelligent reflecting surfaces for 5G and beyond wireless communications. If you have any details, or if you would like to get in touch with me, you can mail me at this email address, and you can also navigate to the next link if you want to know more about me. Okay, so the broad topic for this week will be on Fourier transforms. Okay, so as usual, the first part of the today's session will be to do a quick summarization of week seven's lectures. Okay, so now if you recall, in week six, there was an elaborate discussion on Fourier series, which is basically defined for a continuous periodic signal. Okay, you can, so the underlying theory is that any continuous periodic signal can be represented as an infinite summation of complex exponential with appropriate coefficients, right? So that was basically a Fourier series. But now, if your signal is aperiodic, okay, so then what is the notion of the Fourier series? So basically, in that case, you have something called a Fourier transform. So basically, as you see here on the screen, Fourier transforms are basically defined for continuous time aperiodic signals. Okay, but that does not mean that you cannot define Fourier transform for a periodic signal. You can define, but the Fourier transform basically covers both general transform, the umbrella of both aperiodic and periodic. But in general, we call it aperiodic here because we say periodic for Fourier series. Okay, so the definition of Fourier transform is given by this equation. Okay, so basically, if you integrate minus infinity to plus infinity, x of t into e raised to minus j omega t dt. So if you recall, this is exactly looking like, it looks like your Laplace transform definition, except that instead of j omega, we had the script s in Laplace transform. This is also basically, you can view it as a Laplace transform. Yeah, we will give the connection between Laplace transform and Fourier transform in a while. Okay. So this is basically a definition of your Fourier transform. So omega is basically your frequency, your angular frequency. So essentially what Fourier transform does is it will measure the amount of signal present as a function of your angular frequency omega. Or in other words, it basic Fourier transform gives you a representation of the time domain signal in the frequency domain. Okay, so this is basically your general definition of Fourier transform. So here omega is an angular frequency, that is omega equal to 2 pi f, where f is your radial frequency. Now suppose if I want to define my Fourier transform with respect to directly radial frequency, then basically it is just replace omega here by f, and here omega expand omega as 2 pi f. That's all. Okay, so you are in terms of radial frequency, your x of f can be defined as integral minus infinity to plus infinity x of t into e raised to minus j 2 pi f t dt. Okay. Both are valid representation, but I think professor had confined to the first way of defining the Fourier transform, which is equally acceptable. Okay, both basically are the same, just that you have an extra additional constant 2 pi that differs in the domain, omega domain versus f domain. Now, if I have defined what is a Fourier transform, then it also means, it is also necessary that I need to understand how to get the inverse Fourier transform. That is, if I given a time domain signal x of t, if I've computed x of omega, now given x of omega, how do I retain? How do I basically extract my time domain signal x of t? And that is precisely carried by your inverse Fourier transform. So inverse Fourier transform takes input x of omega, and you do this integration, and you get the output as x of t. So x of t equal to 1 by 2 pi integral minus infinity to plus infinity x of omega into e raised to j omega t into d omega. No, the integral variable is omega. That is, you assume that you know x of omega for every omega, and then compute this integral, you will get x of t. Okay, and different values of t in this exponent here will give the corresponding x of t at that particular time. Okay, in terms of radial frequency, if I want to compute my inverse Fourier transform, this is the expression. Okay, exactly same as above, except that you will now not have an additional 1 by 2 pi um, factor sitting in front of the integral. Okay. Now, what is the spectrum? Okay, spectrum is generally a term that is used to denote a function of frequency. Okay, for example, x of omega, right? This is your Fourier transform. You can decompose this as x of omega. X of omega is a complex number because you see, even if x of t happens to be a real number, even if x of t is real, this e power minus j omega t will introduce a complex, will make this number complex in nature. So x of omega is in general a complex number. And so any complex number can be decomposed as an amplitude times a phase, like z equal to x plus jy can be written as some magnitude mod z into e raised to angle of z, right? This is basically any complex number can be represented in this polar representation. Similarly, you can represent your x of omega, which is a complex number, also an amplitude part times a phase part. Okay, this amplitude part as a function of omega is called magnitude spectrum, and the phase part, angle of x of omega as a function of omega, is called the phase spectrum. Okay, now for real signals, you can show that your x conjugate of omega is equal to x of minus omega. Okay, if you recall your Fourier series properties, we had seen something like this. As a result of this, what happens is your mod of x of omega is same as mod of x of minus omega. This is called the even symmetric nature of your magnitude response. And angle of x of minus omega equal to minus of angle of x of omega. This is called odd symmetric nature of your phase response. Okay, so this basically we have seen even for a Fourier series. We are now just extending that to Fourier transforms, which is applicable for even for a aperiodic signal. That's all. Okay, again, similar to Fourier series, we have some conditions known as the Dirichlet conditions for convergence. That is, convergence means when does this integral really converge? When does this integral exist? Okay, you need to have some maybe some criterion to say whether this integral will even give a finite number, finite complex number, right? So basically, to check that, there are something called the Dirichlet conditions. These conditions, again, mind that they are not necessary conditions. They're just sufficient, meaning that if the Dirichlet conditions are satisfied, then you can show that your Fourier transform will always exist. But doesn't mean that if you want the Fourier transform to exist, they should necessarily satisfy all these conditions. It's possible to have signals for which Fourier transform will exist, but it might not satisfy Dirichlet condition. On the other hand, if something satisfies Dirichlet conditions for sure, then definitely its Fourier transform will exist. That's the meaning of saying that Dirichlet conditions are sufficient. It is just sufficient to say that Fourier transform exists, but it is not mandatory. That is, it's not necessary that for existence of Fourier transform, these three conditions must be satisfied. The must is not something that I'm imposing. Okay? So similar to Fourier series, they are all again the same. That is, your x of t must be absolutely integrable. X of t must have finite number of maximas and minimas, and x of t must have finite number of discontinuities. Okay, these three are same as what we saw in Fourier series. Okay, now comes basically the related point, which relates the Laplace transform with the Fourier transform. Okay, so Laplace transform of a signal evaluated at s equal to 0 plus j omega gives the expression for Fourier transform. So basically, if you correct, am I audible now? Hello. Can you confirm if I'm audible? I think I was in outage for a moment. I mean, my internet was not proper.
Yes, sir. Yes, yes,
Okay,
sir.
okay. Okay, so basically, we know that S equal to sigma plus j omega. That is basically any S domain complex number can be written as sigma plus j omega. Now, what I'm saying is, if sigma equal to 0, that is the real part of the complex number S equal to 0, then what you have left out is just S is equal to j omega. And precisely at S equal to j omega, if you just substitute S equal to j omega, in the definition of Laplace transform, you get a definition of Fourier transform, right? That means the Laplace transform evaluated at s is equal to 0 plus j omega will give the result which is exactly the same as the Fourier transform of the same signal. Okay, this is basically a relationship between Fourier transform and Laplace transform. Okay. Next is the properties of Fourier transforms. Just like how we had properties of Laplace transform, properties of Z transform, properties of Fourier series. Similarly, we have properties of Fourier transform also. Okay. So the first property is called the linearity property. That is, if I have x of a times x of t plus b times y of t, the corresponding Fourier transform will be a times x of j omega plus b times y of j omega. So here x of omega or x of j omega both mean the same. Okay, x of omega and x of j omega both mean the same. So you see here x of t gives a Fourier transform x of j omega or x of omega. Both notations are same. So the source of this material is, so reference again, it's Oppenheim. Okay, Oppenheim chapter number 4. Fine. That is a linearity property of the Fourier transform. Now time shifting property. So x of t minus t naught will have the Fourier transform in terms of x of j omega as e power minus j omega naught omega t naught times x of j omega. Basically, this time shifting will give a phase shift in the frequency domain or the Fourier domain. Now frequency shifting. If I modulate my, or if I multiply x of t with e raised to j omega naught t, that will correspond to a frequency shift in the frequency domain. X of omega minus omega naught. Conjugation. X conjugate of t will give a corresponding x conjugate of minus j omega. Okay. Now time reversal. That is x of t. Instead of x of t, if you have x of minus t, then there will be a corresponding frequency reversal in the Fourier domain. That is x of omega will become x of minus omega. Now time and frequency scaling, that is x of at, okay, will give rise to a corresponding frequency scaling. So this is called time scaling and this is called frequency scaling. Okay, because your omega is also becoming scaled by a factor of a. So here x of at means it is compression, correct? And x of omega by a means it is expansion. Okay, let me write it down. Compression.
Sir, it is compression of expansion. X of AT.
It is compression when a is greater than 1. Okay. When a is greater than 1, only then it is compression. Similarly, if a is greater than 1, this is expansion. Okay or not? Is it okay? Or you want me to explain?
Sir, its value will be decreased frequency domain. Value will be
okay. Let's take an example then. Okay, so basically, oops. Okay, example.
more than 1.
Yeah, more than 1. Yes. Let's say x of t is something like this. Okay, minus 1 to 1 x of t as respect to t, and amplitude is 1. Okay, now what I want to do is I want to compute x of 2t. What is x of 2t? Say here a is equal to 2, which is greater than 1. Okay, let's try to understand. Let's try to plot this. Okay, so now what I want you to understand is, first let me write x of t mathematically. So x of t is nothing but 1 if t is greater than or equal to 1, 0. Sorry, this is t is between 1 and minus 1. 0 else. Okay, this is basically your mathematical characterization. Maybe I'll make the amplitude as 2 for you to not get confused. So this is 2 if t is between minus 1 and plus 1, else the value takes 0. This is basically, let's say example x of t is this. Now I want to say what is x of 2t. Now basically 2t means, what does it mean? Your x of 2t will be equal to 2 if 2t is between 1 and minus 1, and 0 else. Do you agree?
Yes, sir.
What does this mean? This means 2 if t is between minus half and plus half. 0 else. What does this mean? X of 2t is nothing but 2 from minus half to plus half. Now you see your earlier signal was between minus 1 and plus 1, but now it became minus half to plus half. Is it a compression or an expansion?
It is compression.
Yeah, because this was larger interval. Now I've compressed that to a smaller interval. Interval is only one. This length is only one now. But earlier this length was 2. Okay. So whenever your A, the scaling factor is more than 1, you will have compression of your signal. Okay. This is what I told here. X of AT is basically compression whenever A is greater than 1, and expansion. So here it's expansion because A is getting divided. Okay. A is getting in the division. That's why it is expansion for A greater than 1. Now convolution operation. Okay, whether it is when you have two signals x of t and y of t, if you convolve both of them, then their corresponding Fourier transform will be multiplied. That is basically your convolution property. Now multiplication property. If I multiply both the time domain signals in time domain, how will the corresponding frequency domain signals be? This integral. This is, if you recognize this properly, this is actually nothing but convolution. Okay, basically what I'm saying is this is convolution in frequency domain. That is, if I multiply two signals in time domain, their corresponding frequency domain Fourier transforms will get convolved. You need to convolve both the Fourier transform, and the resultant signal x of some y of some z of omega will be the resultant Fourier transform of the signal x of t into y of t multiplication. That is what it's a very, you see the nice duality. If I convolve in time domain, their corresponding Fourier transforms will get multiplied. Similarly, if I multiply in time domain, their corresponding Fourier transforms will get convolved. So this is basically dual property. Now differentiation property in different d by det of xt will give a corresponding omega times x of j omega. I mean j omega times x of omega. Okay, so basically omega multiplies your x of omega. Integration, basically it is just x, your omega gets divided. It's 1 by omega times x of omega plus this term. Similarly, you have differentiation in frequency. That is, if I multiply t into x of t, you will differentiate your Fourier transform, and so on and so forth. Okay, and these 4.3.3, all these you can verify on your own. For example, if x of t is a real signal, this is something that we showed before. X conjugate of minus omega is equal to x of omega. Okay, that means this is basically your your magnitude spectrum is even symmetric, and your phase spectrum is odd symmetric. Okay. Similarly, these are some properties which I'm not covering now, but you can read Oppenheim book to understand these properties better. And this is worth reading. It's a very nice. These are very good properties. You can always note. Okay. Now, one more property which is missed out in this box, but which was discussed by professor, is a duality property. That is, let's say small x of t is a signal or a function whose frequency is Fourier transform is x of omega. Then, I mean, here x of omega is capital X of omega. If I construct a capital X of t, that is the same function I construct in the time domain, then the corresponding frequency Fourier transform will be small x of minus omega. That is, my x of t, small x of t, the same function in frequency, but a flipped version. Instead of omega, it is minus omega. So this is called the duality property of the Fourier transform. Okay. And parcels relation. Parcel relation is where, see, integral minus infinity to plus infinity x of t whole square dt equal to 1 by 2 pi minus infinity to, yes.
Sir, how we can represent x omega, the capital X of t, x of omega, capital X, how we can represent?
Capital X. So you want to understand this properly by an example?
Yes.
Okay, okay. I will do it. I will do it. I will tell what this means. I will tell you what this means. Okay, so this Parsel's theorem exactly basically tells that your energy in the time domain is same as the energy in the frequency domain. Energy remains same in both time and frequency domains. Okay, okay. Let's now give an example of what I mean by duality. Okay, let's say your x of t is nothing but a rectangular signal, same as the above example, x of t from -1 to 1 with amplitude 2 and time. Okay, let's say this is a rectangular signal. Okay, now you can show that your Fourier transform x of f. I'll just write it in terms of, okay, maybe I should write x of omega, no problem. Will be a sinc function. Okay, will be a sinc function as a function of omega. Okay, is it fine? Let's
Yes,
say
sir.
this is, let's say now what I'm saying is, suppose you have some y of t equal to sinc function. So the basically your x of omega is equal to sinc function. I'm not writing the exact, exact expression. You will have some constant c1 times sinc of c2 into omega. This is the exact expression where the number c1 and c2 are, you need to find out from the definition of Fourier transform, the integral. Okay, but let's say there is some, you evaluate the Fourier transform of this rectangular signal and you get this sinc function as the Fourier domain. Now suppose if I want to take a time domain signal which is already a sinc function, okay, sinc t, that is basically your y of t itself is a sinc function. Do you understand? Now what I'm saying is, if I compute the Fourier transform of y of omega, this will be, this is nothing but small x of minus omega is what I'm saying. That is, it will be something like this. Y of omega will be small x of minus omega. I mean, of course, there's a 2 pi constant. I'm just, these constants for a moment you ignore. Let's say that is c3 times x3, x of minus omega. So c3 times x of minus omega. Small x times omega. But now this is a rectangular signal, right? So it's a rectangular signal will have, so basically this is basically even symmetric. So x of minus omega is same as x of omega. The same as just this. Flipping of a rectangular signal about the yx doesn't change. So y of omega equal to just x of t. Did you understand what I'm telling? Now do you understand? Is it clear? This this is called
Yes.
the dual property. That is, if I have a time domain signal something like this, and let's say it has a corresponding frequency domain function like this. Suppose if I treat a time domain signal which is of this form, okay, let's say a sinc function, and if I ask what is the Fourier transform of this, it will turn
I
out that
understand.
it is the flipped version of this signal.
Yes.
That is what I mean by dual property. Okay, so this is called the duality property of the Fourier transforms.
Yes.
Of course, these constants C1, C2, C3 and all, you need to properly evaluate. The integration is there, right? Definition of Fourier transform. Evaluate the integral and you have to find what C1 is, what C2 is. These are constants. Okay, let's now go back to our discussion. So that was basically all the properties of Fourier transforms that we had studied. And now there are some Fourier transform of common signals. I'm not going to go through these in detail. It's again available in Oppenheim or in my notes also. You can just go through it. Okay. Now comes the frequency response of a system. Let's say you excite a system with input x of t with an impulse response h of t, and you get the output as y of t. Then essentially, what by the convolution property of Fourier transforms, your output signal's Fourier transform, that is y of omega, will be the multiplication of the Fourier transform of x of t and that of h of t. That is x of omega multiplied by h of omega equal to y of omega. Which means from this you can find h of omega as y of omega divided by x of omega for every omega. Now this is called the frequency response of a system. Okay, and for such kind of system, x of t equal to e raised to j omega naught t is what is called an eigenfunction. Okay. Now there is another notion of what is called a distortionless transmission via a system. What does it mean for a system to be distortionless? It means that the output of a distortionless system, y of t, must be a scaled, that is a scaled and a delayed version of your input. Okay, that is, thus the output can only be allowed to be scaled by some number, scaled by some number k, and it is allowed to just delay your input signal. It should not do anything else to your input. If a system does only scaling and time delaying, such kind of systems are called distortionless systems. Okay, what is the properties of such kind of systems? So you can show that the magnitude spectrum of the frequency response of such systems will have a constant, basically your magnitude response. These systems must have constant magnitude response. The frequency response of these systems must have a constant magnitude response, and the frequency response of such kind of systems should have a linear phase response. Okay, this should be a constant and this should be a linear. If these two conditions are satisfied, then such kind of systems are distortionless systems. Now, the last topic of this week was on filter design. Okay, filter means what we all know, from basically that a filter will basically only separate out the desired components. For example, we have something called water filter, where you have so much of dirty water, or which will contain so many contaminants and so on. But so what does a filter do? It will not allow any kind of dirt particles to percolate through in. Okay, all the dirt particles will sediment in the top layer, and only the drinking pure water will get into the second layer. That is called a filtering operation. So in the context of systems, okay, a filter is something similar to an allowing of only desired components. Here, the desired components are measured with respect to frequencies. That is, the filter will allow only certain frequencies to pass through the system. So so the one kind of system, such kind of system is called the low pass filter. Okay, low pass filter. What does a low pass filter mean? Let's say there is a signal which has multiple frequency components, and if you give input to a system with such kind of multiple component signal, then the output will only contain the signals in the low pass. That is something like this. Okay, signal frequency components less than a particular threshold. Any other frequency component of the signal higher than a threshold will be completely discarded by the system. The output will not contain any higher frequency component. Such kind of systems are called low pass filters or low pass systems. How will the frequency response, the magnitude frequency response of such kind of system look? It's given by this figure, right? So basically what this figure says, it's like a window. Okay, so between two frequencies, minus omega to plus omega c, minus omega c to plus omega c, the frequency response is 1, and everywhere else it is 0. So what it means? It means that the output of the signal will only contain frequency components from minus omega c to plus omega c, but not anywhere else. That is called the low pass filter characteristics. Now, contrarily, the other filter is called the high pass filter. That is, it doesn't allow any low frequency components to be present in your output signal. Only high components will be present. That will have something like this. So between minus omega c to plus omega c, the frequency response of the system should be 0. Everywhere else it should be 1. Okay, so such kind of systems are called high pass signals. Now this omega c that comes in, let's say, low pass or high pass, is called the cutoff frequency. That basically threshold frequency beyond which the output signal will not contain any desirable frequency. For example, in case of low pass filter, any frequency above this cutoff frequency will be not present, will be absent at the output. Similarly, before any frequency that is less than omega c in case of a high pass filter will be absent in the output of such system. Similarly, band pass means I want to have the output should contain frequency only within a particular band. Let's say between omega 1 to omega 2. Everywhere else it should be 0. From 0 to omega it should be 0, and omega 2 to infinity also 0. Only the frequency content should be from this band. Okay? Then that such kind of systems are called band pass. Such kind of filters are called band pass filter. That is, it passes only a particular band. That's why it's called a band pass filter. This is called a high pass filter because it passes all the high frequencies. Now this is called a low pass filter because it passes only the low frequency bands of the output to the output. Similarly, there's something called band stop filter, which is also called the notch filter. What it does is it will allow all frequencies to pass through the system except a particular band. Okay, it's exactly the complement of your band pass. It only passes a particular band, but band stop will only reject a particular band. Every other frequency components will be passed to the output. That is called a band stop filter. Okay. However, practical these are called ideal filter. Why ideal? Because if you have, let's say, omega 1 plus some very small constant, you'll have a unit response, magnitude equal to 1. Any number which is just less than omega 1, omega 1 will be having a 0 response. It's like a sharp transition here. But you cannot realize such kind of systems in practice. So we go for something called the practical filters. Okay, basically in practical filters, the idea is that you will make this sharp transition to roll, to have a kind of a roll off. Okay? And this roll off, this region is called a transition band. Okay, the transition band is something like a gray area where you will get the components of signal falling in this frequency will be present in the output, but they will be attenuated because you see it is not equal to 1. Here it is falling off. Here it is equal to 1, but here it is not equal to 1. So they will get attenuated, but still they will be present in the output. And once it goes beyond omega dash, it is completely absent. Any frequency beyond omega dash will be completely rejected by the filter. So this is an example of a practical low pass filter. So this was basically the gist of this week's lecture. Are there any questions or doubts? Okay, so I assume everything is clear. Now let's start solving some problems. So basically, yeah, tell
Sir,
me.
I
Hmm.
have the Fourier transform can be used for periodic signals.
Yes, you can define. Yes, definitely.
The aperiodic and periodic.
Yes, yes. It's
In,
possible to write a Fourier transform even for a aperiodic signal. Periodic signal.
yes, sir, but usually it is uh, aperiodic.
Sorry, I didn't hear you properly. What is aperiodic?
Sir, but usually it is used to define the aperiodic signal, sir.
Correct, correct. So basically, the reason is aperiodic signals can be any arbitrary signal, but periodic will always have a structure that it should repeat with periods. That's why generally we give the term aperiodic as a as a way to define Fourier transform. But it's possible to define Fourier transform even for a periodic signal. Okay, you can know
Okay.
there's Fourier transform. Just nothing. Just evaluate the integral. Doesn't matter. You will always be able to find Fourier transform for periodic signals also. Okay. So what I'm going to do is this week and next week we are going to solve problems only on Fourier series and Fourier transform. So this week I will finish Fourier series, and next week we'll do only Fourier transforms. Okay. So now, what we will do is we will quickly recapitulate one question which we did last time. Okay, let's say there's a periodic signal as you see here, like it's a square wave From 0 to t naught by 2, it is amplitude 1, and from t naught by 2 to t naught, it is amplitude 0. Okay, and this kind of a structure repeat itself throughout the entire time domain. Okay, so it's a periodic signal with fundamental period equal to t naught. Okay, then the question that we solved last time was, what is the complex exponential Fourier series of such kind of signal x of t, and also a corresponding trigonometric Fourier series. Okay, let's quickly recapitulate this because we will use this result today in some of the problems. So if you recall, your Fourier series definition was that your x of t should be represented as summation k equal to minus infinity to plus infinity ck into e raised to jk omega naught t, where omega naught is nothing but 2 pi by t naught, where t naught is the fundamental period. Okay, now basically you know omega naught because t naught is given in the question, that is the fundamental period is equal to t naught. So that means omega naught is something known. What needs to be found is what is ck. If I know ck, then the complete characterization of Fourier series is done. Okay, so now what you do, just go back to the definition of ck. Ck is basically defined as this integral, if you remember, 1 by t naught, where t naught is a fundamental period, integral over a fundamental period, that is 0 to t naught, x of t, e raised to minus j k omega naught t, where k is the same k for which you are computing the ck, into dt. Then what happens? Here x of t is over from 0 to t naught. From 0 to t naught, how is the signal? It is equal to a between 0 to t naught by 2, and between t naught by 2 to t naught, it is equal to 0. Okay, that is what I'm computing here. So for 1 by t naught, 0 to t naught by 2, it is x of t is nothing but a, and from t naught by 2 to t naught, x of t is equal to 0. So second term is essentially knocked off. It's completely equal to 0. Only first term survives, which is exactly this term. 1 by t naught, integral 0 to t naught by 2, a times e raised to jk omega naught t dt. So a is a constant, put it out, that is a by t naught, and the integral remains. Now just integrate the e power x form. So what is this? E raised to minus jk omega naught t divided by minus jk omega naught. Limits are from 0 to t naught by 2. Now just now basically expand the limits. Okay, so basically t naught by 2 you get this, and e power 0 is just 1, and then you can show that you will get something like this. But what I know is that omega naught is equal to 2 pi by t naught, which means omega naught t naught should be equal to 2 pi, because I just take this t naught here. So omega naught t naught equal to 2 pi. Substitute this in this expression. For example, there's omega naught t naught here, there's omega naught t naught here also. Then what I get? I get something like this: a by jk 2 pi into 1 minus e raised to this guy. But this is nothing but really, minus 1 power k. That is basically this number. So then what it means is that whenever your k is not equal to 0, okay, and when k is an even number, this minus 1 power k will be equal to 1, because any even power of minus 1 is equal to 1. So then 1 minus 1 will become 0. Therefore, any even k, ck is equal to 0. Whenever k is odd, that is, you can write k is equal to 2m plus 1, then minus 1 power k will be equal to minus 1, then 1 minus of minus 1 will be equal to 2, and that 2 will cancel with the denominator 2 here. So what you have is a by jk pi for odd values of k. Okay, so this is for k not equal to 0. For k equal to 0, what you do? Go back to the expression. You remember this was the expression for ck, and then when you put k equal to 0, this will just e power 0 will go off to 1. So it's just 1 by t naught into integral 0 to t naught x of t dt. And this is same as this guy, because second term from t naught by 2 to t naught is equal to 0. So the integral is only from 0 to t naught by 2, where the x of t is equal to a. So evaluate this, you get c naught equal to a by 2. A by 2. So I have c naught equal to a by 2. And for any other ck, whenever k is even, it is equal to 0, and k is odd, it is equal to this number. Just substitute for all these expressions in your first expression for Fourier series. What you get is this guy, that your x of t is equal to a by 2, which is contributed due to your c naught, and c2m is anyway 0. 2m because it's an even number, 0. But whenever odd, it is equal to this number. Okay, then this is basically your, all this is nothing but ck. But I'm writing k is a odd number, so it is m plus 1, 2m plus 1. It's an odd number. And similarly, this is basically your k. which is nothing but omega 2m plus 1 omega naught t. So this is basically your Fourier series expansion of the square wave that we saw above. Okay. I hope this was clear. From this, we will move on to the second question for today.